Wind turbine systems use renewable energy to convert kinetic energy from air into mechanical and electrical forms. Although it is not the most efficient energy alternative, wind energy does account for 10% of the world's electricity supply in some areas around the globe. Featured below are 4 models which we use to compare for our windmill presentation. Model A. Cost of production 200 riyals. Materials were easy to obtain, but it was difficult to assemble together. The windmill required too much carpentry and, as quoted above, used too much of plastic. This wasn't eco-friendly. Model B. Cost of production 50 riyals. This was the cheapest windmill to make. It had a tail which enabled a 360-degree rotation such that the windmill moved in the direction of the wind. This enabled maximum frequency. However, it wasn't durable and again required a lot of carpentry. C. The Savonius windmill. This windmill, unlike the other two, was a horizontal windmill. Cost of production 100 riyals. It was unique but less efficient than the vertical windmill. Also, it required too much carpentry, which seemed complex and difficult to make. Model D was a combination of all other 3. The cost of production was 70 riyals. It combined the idea of the tail from Model B and uses a fewer blades than Model C and B and A. Since there are only 3 blades, it is more efficient than Model A and B. It was cheaper than Model A as well. The blades were more durable since they were made from PVC, and it worked like Model C since it could move in the direction of the wind but only with greater efficiency. We chose Model D. The windmill was then designed on SolidWorks, and as you can see, it was very easy to construct and did not require strenuous work. With the help of YouTube video, we learned how to cut the blades from PVC. And as featured above, the windmill blades were cut in such a way that it enabled maximum surface area and minimum air resistance. This helped it sweep through the air, just like the way the wings on a plane would. The people then used wood for the base, and as quoted here, carpentry was used to a very minimal amount, just for the attachment of the basic base. Later, the team members met in a lab, just for drilling and sawing purposes. This too did not require a lot of effort and time. This is the final blade. The plastic was attached to the bearing to enable a 360-degree rotation, and a tail was fused onto this with the help of screws. The generator was then attached on top of this blade as seen. Assembly and disassembly of this prototype was as easy. It was assembled in such a way that it would fit into a box of volume 900 cm3. This met one of the project's main objectives. The blades are attached to the generator. The windmill can now move in any direction depending on the direction of the wind. This is the disassembly process. Shown here is the green spine which we picked, as it would be the most suitable location to set up the windmill prototype. The blades can move clockwise and anti-clockwise. MATLAB readings above show how wind speed affects the power. This is the final SolidWorks model of the blade and the windmill. Thank you. Credits to Rachit Kumar for making this video, Kumar and Nisa for assembling the models together, and Talha for contributing towards the assembly and the disassembly of the prototype.